Record. All right. So here we go. Happy Friday. Happy post-Halloween, I guess. Just because we were talking about it before. We're going to do linear equations today, just kind of brush up on linear equations, inequalities, and that kind of stuff. And it's kind of leading us into matrices next week. And so have you guys done any matrix stuff? But it sounds cool, right? So that's something to look forward to. And so we'll start matrices next week, but there's no lecture. I'll just post a video. It kind of depends on what we get through on Monday, today/Monday. So I'll kind of play it by ear, but it'll be more matrices, just seeing how far we'll get. And so I'll post a video for you to watch at your leisure, but it is the Friday before a long weekend, so I wasn't going to mess around with that. So obviously no classes on the Monday, the 11th. And then I'm kind of rethinking my structure. So it's okay. We will do 6 and 7, but I was told I can cut 8, 9, and 10, but then I'm like, well, what should we be doing then? Chapters 8, 9, and 10, which is like 8, 9, 10. I don't know. They're like, oh no, you don't need to do that. Well, what should we be doing then? So that's why we might stretch out matrices a little bit longer. But, or we can just do them. They're pretty fun. So, guess we'll see what I decide. All right. Hopefully some of this will just be review, nice and breezy. And if it's not, then that's okay too. Linear equations, linear just means a straight line. And so linear equations have the form of y equals mx plus b, which might ring a bell, right? Where we know that m is the slope and b is the y-intercept. Usually we just call it the intercept because we rarely care about the x-intercept, but it's technically the y-intercept. And so we're going to be working with lines. Luckily, kind of a lot of things can be represented by lines or linear equations. Linear equations refers to where we don't have powers on our variables. We just have x, y, z, that kind of thing. And so right here we have y and we have x. We don't have an x squared, for example. That's a quadratic. And so just kind of linear functions. So plotting, graphing. I heard some, no, I don't want to do it. We're not going to do the graphing like, oh, you have to shift it over and you have to stretch it and then you have to flip it upside down. We're not going to do that because I also hate doing that. And I just make software do that.
You're saying there's no graph like that.
Well, there will be, but they're different. Yeah. The stuff that we'll do today, I'll test you on. But you'll see. It's just drawing lines. That's it. So we need to know how to draw a line. All you need to do, or all you need to draw a line is you need 2 points on the line. My go-to move is, well, it's usually easy to find the y-intercept, right? I set x equal to 0 and I solve for the y-intercept, and that's one of the points on my line. Then you're going to plot a second point. If you have 2 points and you have a straight edge, so usually I kind of just take my paper and use it as my straight edge, kind of like a ruler. It's, I don't know, it's kind of hokey, but it works. So if I need to draw a straight line, then all I need are 2 points on that line, and then I connect them and I extend the line, and then I'm done, right? And so I do need you to be able to draw straight lines. And so here, I realized I drew these, and then I'm printing in black and white so you can't see the colors. And so then, but you should have labels because I photocopied kind of old school L1, L2, L3. And so what we're going to do is kind of reverse engineer the lines from the points on each of these. Okay. It'll be pretty clear pretty quickly which one's which. But one of the things you could do that I'm going to avoid doing in this case, because I'm lazy, and that's the only reason why, is you could rearrange these into y equals mx plus b form, right? That might be nice. I'm just going to leave them as they are. No, they're not very complicated. And so what am I going to do? First thing I'm going to do here is I'm going to figure out what y is when each of these, when I set x equal to 0. X equal to 0, all right? Boy, that's too big of a highlighter. Here, x equals 0. Each line is going to pass through the y axis at some point, and that's at x equals 0. And so I can really figure out which line is which just using the y-intercept because they're all unique, right? As opposed to if I use the y-intercept, as opposed to if I use the x-intercept, then these two are not unique, so I'd have to keep going. But let's just, for completeness sake, say that 0 plus y is equal to 3. Well, then y must be 3. Which means that 0, 3 is on this first line. Right? If you don't have the lines, right, let's kind of work it that way, then you would have this point on the line, right? So let's pretend that you don't have the line for a second, and let's do the same thing and let y be 0. Then you have x plus 0 is 3. So then x must be 3. When y is 0, that's here. Or I should write it on that side because I need more room on the other side. And so then I'm ready to commit that, okay, that line must be L1. Because it has both those points on it, and none of the others do. If I do the same thing for the next one, if I let x be 0 and 2x minus y is equal to -2, I get 2 times 0 minus y is -2, which means -y is -2. So when x is 0, y is 2.
L1 and L3 for the first question, x plus y.
Oh, this line here is L3. And L3, when x is 0, y is -1. But we found when x is 0, y is 3. So it has to be this one, taking both points into account. Right? Here, if we had only done this, then yeah, it could be L1 or L3. But because we also know the second point, or the first point rather, at x equals 0, then it has to be L1. So then here, just knowing when x is 0, y is 2, well, the only one that makes that happen is L2, so I'm kind of ready to commit to that already. But for practice, right, let's figure out what x is when y is 0. 2x minus 0 is equal to -2. So 2x is equal to -2, which means x is equal to -1. Which tells me that the only line where both of those points are true is for L2. Process of elimination tells me that the last one must be L3 then. And so, but let's just confirm, if I let x be 0 in x equals 3y plus 3, then I have 0 is 3y plus 3. So -3 is equal to 3y, and so y is equal to -1. Which checks out, because if we look at L3, we saw that, okay, the y-intercept for L3, this is L3 here, is at 0, -1, and so that's what we were expecting. And we're also expecting, when I let y be 0, I'm expecting y to be, or x to be 3. So let's see here, x is 3 times 0 plus 3, which means x is 3. So I'm ready to commit that that's going to be line 3. Nice. You can pick any points on the line, right? It depends on if I give you a grid, right? Maybe pick values of x that are in the grid so that you can easily kind of map them. Or easy to calculate, right? X equals 0 is usually very easy to calculate, and not as easy, but somewhat easy is y equals 0. Setting y equal to 0 and solving for x is also relatively easy. And so that's why I chose those, but you can really pick any 2 points or values of x and solve for y, and then plot those points, connect them, extend the lines, because lines keep going to -infinity, +infinity, right? And so, and then you've drawn a line. Any questions about that? Yeah. A refresher on inequalities. Now, I know I don't love inequalities, so I tend to just treat them as equal signs, but we need to remember that if I'm multiplying or dividing by a negative number, then I have to switch the sign, okay? And so the formal properties are these. And so I'm using just less than. This is less than. Because it makes an L. I had a student tell me that, which is kind of, I don't know, it was way too late for me. I struggled with inequalities. So it's the one that makes an L, and you're going to read it as less than, right? So A is less than B, right? And then the other one is the opposite. That's nice. So somewhat binary, right? We have less than or equal to and greater than or equal to, but of course those just include the endpoints as opposed to excluding the endpoints. We've already talked about those briefly when we talked about sets. And so we've seen inequalities before, but here I realized I hadn't stated the rules officially. So if A is less than B and C can be any number, then if I add C to both sides, the inequality stays the same. A plus C is less than B plus C, right? Same thing if I subtract C, it'll just stay the same, right? And you can pick values of A and B that satisfy this criteria. 2 is less than 4, right? And then if I let C be 1, 2 minus 1 is less than 4 minus 1, still true. So this one, I'll just say no change in the less than, right? If A is less than B and C is positive, oh, now it's too small. Then if I multiply each side of the inequality by C, right, then there's no change in the inequality. No change in the inequality. However, how can I highlight this? Hopefully it's not too dark. Kind of. Do green, even though that's kind of positive. But anyways, if A is less than B and C is negative, right? Whether it's a fraction, so division, or if it's a whole number, then that's just a number, then A times C becomes greater than B times C, okay? And so this here switch less than to greater than. Let's do just a quick example, right? When we multiply an inequality by a negative number, we need to reverse the inequality sign. And just remember, multiplying, well, division is just a special case of multiplying, right? So division is just multiplying by a fraction. Maybe I'll add that. Remember, division is just multiplication. Oops. By a fraction. Just like subtraction is just special case of addition, it's just adding a negative. So if we let A be 4 and B be something larger than 4, let's say 10, C has to be negative. So let's let C be, I don't know, -2. Just pick anything. At first, 4 is less than 10. I think we all agree that's true. So 4 is less than 10. C is -2, which is negative. So both those conditions are satisfied. So now if I take A times C, I'm just going to jump straight to the is greater than B times C, because I don't want to write something false and then correct it later. So we've switched the inequality here. And so now I have 4 times -2 should be greater than 10 times -2. -8 is greater than -20. Think about a number line, right? On a number line, we have 0 over here. I've got -8 and I've got -20. -8 is larger than -20. Negatives are weird though. Okay. Any questions about inequalities? We've got an example. So we can solve inequalities, we can treat them as equal signs until we're multiplying or dividing by a negative, right? And what's nice about inequalities, just like equalities, you can always go back and check your work, pick some values of x, and put them in and see if it's true, right? And so if we have to solve this inequality, let me just use a different color so that they stay kind of together. I was pretty cheap on the spacing here, I'm realizing. Although when I did it on mine, I even checked the spacing. Maybe it's just on my iPad. I need more virtual space. So what we're gonna do, just like solving for an equation, we can solve an inequality by moving everything over to one side and just leaving x alone on the other side. So we're slowly gonna pick away at this thing and try to solve for x. And so I have negative 3x plus 2 is greater than or equal to negative 1. Chipping away and trying to find what x is. X, I'm going to subtract 2 from both sides. That's safe. Oops, negative 3x is greater than or equal to negative 3. And so negative 3x is greater than or equal to negative 3. So I can divide both sides by negative 3, but then an alarm bell goes off and I have x is greater than or equal to negative 3 divided by negative 3 makes 1. And I want to highlight that switcheroo there. So now the result is that x must be less than or equal to 1, which you can check. You can pick a value less than or equal to 1 and plug it in. I'd probably not choose 1 just because it's going to be on the cusp, but let's do something less than 1. Let's do 0. That's nice. So you can check by let x be 0, then negative 3 times 0 plus 2 is 2, which is greater than or equal to negative 1. So that's true. You could leave it at, it doesn't specify how it wants the answer, so you could leave it as x is less than or equal to 1, which is probably what I would do. Or you could use interval notation, which would be negative infinity to 1 square bracket, right? Because it's up to and including 1. All the values up to and including 1. Any questions? Okay. Determine whether or not the given point satisfies this inequality. So we have y is greater than or equal to negative 2 over 3x plus 4. So we have an xy coordinate. Right? And so I'm given a value of x and I'm given a value of y, and we need to see if it's true or not. So what I'm going to do is I have x is equal to 3 and y is equal to 4. So what I want to know is if 4, and if I'm not sure, sometimes I put a little question mark. If what I'm doing is checking to see if it's true, right, then I put a little, should do it in here. I put a little question mark up above because that's what I'm checking, right? Is it greater than or equal to 4? And so negative 2 over 3 times 3, which is nice because then it'll cancel. So I have negative 2 plus 4 puts me at 2. 4 is greater than or equal to 2. And So that is, it does satisfy the inequality. How about the next point? If x is 0 and y is 0, then I have 0 greater than or equal to -2 over 3 times 0 plus 4. -2 over 3 times 0 is 0. And then I have 4. 0 is not greater than or equal to 4. So it's not, does not satisfy the inequality. We can graph linear inequalities, right? Things like y greater than or equal to mx plus b, or y less than or equal to mx plus b. Of course, it can be just less than or greater than. What you're going to do is you're going to draw the graph of y equals mx plus b, right? That's going to be kind of your divisor, your borderline, I guess. And then here is where I want to make a note. So for us, when we do it by hand, I want you to cross out the regions that do not satisfy the inequality, because it's going to make it easier later on. However, a lot of software, like if you use Desmos or I took out those assignment questions, but in the assignment, then they want you to highlight the area that it does satisfy. And so for us, I'm kind of open to either, but as long as you tell me which one you're using. And so here, throw away or cross out the portion of the plane that does not satisfy the inequality. An important note, Desmos highlights the area that does satisfy the inequality. For us, just to give you a little bit of a heads up, what we're going to be doing is we're going to be looking at a system of inequalities, so a bunch of inequalities and how they act together. And so then what we're going to want is we're going to want the region where they're all satisfied. That's really hard to do, because then if you're looking at three inequalities, for example, you'd have to figure out the region where all three are shaded. And that's harder than seeing where none of them are shaded, right? So then if it's shaded, it's out. And if it's empty, then you're good. So for us, this is more for doing it by hand. Best for working by hand, which obviously on the test we will be. Like I said, I'm okay with either one. In fact, I used to shade in even when I was doing it by hand, but it gets really messy. And so I was reading this other book, and they recommended to cross out the ones that do not satisfy. And it kind of made sense to me. So I guess I'm kind of trying something new, but yeah, so eventually that's where we're heading. And so that's why we're going to use this method. Let's see how we do it. So again, to graph an inequality or a linear inequality, first treat it like a line. Draw the line, and then figure out on which side of the line this inequality is true, right? That's part of your solution, or that whole region is part of your solution. the opposite side is not, right? And so we're just gonna sketch this inequality. X plus 2y is less than or equal to 4. So first thing I'm going to do is I'm going to sketch this thing. Now it's optional, but let's rearrange this to be just y equals mx plus b, right? And so if I have x plus 2y is less than or equal to 4, solving for y, I get 2y is less than or equal to 4 minus x. So y, no negatives, so we're all good. Must be less than or equal to 4x minus 2. You can simplify that to 2 minus 1/2 x if you want. I'm just going to leave it. Doesn't really matter. We're just drawing it anyways, or sketching it. We're sketching because I didn't want to put in a new graph for this little guy. So let's see here. I'm gonna draw the line. So draw y equals 4 minus x over 2. To draw lines, usually I set up a quick little table like this. Often I let x be 0 and I solve for y. If x is 0, 4 minus 0 divided by 2, I'm gonna go for 2. And then you could even kind of scope out your equation and figure out a convenient value of x. A convenient value of x here is 4, right? Then I get 4 minus 4 divided by 2, but 4 minus 4 is 0, divided by 2 is 0. So then when x is 4, y is 0, right? Just happened to be because it was a convenient value, right? So I guess I accidentally, not accidentally, but found the x-intercept. Yeah. So what I would avoid doing is something like 4 minus 7. What's that? 4 minus 7 is negative 3 over 2. I don't want to plot that. Yeah, but I don't want to draw that. So it's just, what do you want to draw, right? And so what points do you think are going to be easy to draw or relatively easy to draw? Now we're just sketching it, but what do we need? We need a little bit of foresight here, right? On my x-axis, I need at least between 0 and 4. And on my y-axis, I definitely need 0 and 2. It might be nice to have a little bit more, right? So if you're figuring out your axes and what your sketch is going to look like, which is all part of the job here. Again, we are just sketching, so maybe 1, 2, 3, 4, 5, sure. 1, 2, 3, 4. Relatively even. Then I can draw when x is 0, y is 2. And when x is 4, 1, 2, 3, 4, y is 0. Nice. 2 points. I can bend up some paper and use it as a fake ruler. Connect the dots, extend the line. Nice. No, just bend your page. Look at how convenient that is. Try it. You won't be disappointed. Just use any straight edge, the edge of your calculator, whatever. Doesn't. You shouldn't use your lines to find answers anyways. It's just to kind of sketch the feasible set later on. Okay, so we've got the line. Nice. But it was an inequality. So only 1/2 of this line is going to satisfy that inequality, right? And so from here, you, with some practice, right, y is less than or equal to 4 minus x over 2. And so if it has to be less than this, so the y's have to be less than that line. So what's going to happen is, and I better check to make sure, yeah. Y has to be less than or equal to this thing. And so the values that make this true are on kind of below the line. That's hard to see, I think, when you're first kind of starting out with these, right? But what you can do is you can pick some test points, right? You can say, okay, if x is 0 and y is 0, then do I get a true statement? 0 is less than 4 minus 0 divided by 2. That's true, right? 0 is less than 2. I'll add that here. We can pick test points like, well, my go-to is 0, 0. That's nice because it's in part of the region or in one of the regions. And then what's another one that is on the other side of the region? Maybe 4, 2. I can see would be outside the region. If x is 4, then y equals 2 is a point in that region. And so here at 0, 0, we can see, just like we did in the beginning, we can see if it satisfies the inequality. We suspect that it will, just because we have this idea about how this is going to behave. But let's see. 0 is less than 4 minus 0 divided by 2, which is 2, so that's true. 0 is less than or equal to 2. What about 4, 2? If x is 4, y is 2, 2, is it less than or equal to 4 minus 4 divided by 2? It is not. That's not true, right? Or maybe I should do this, which means that, how can I do this? This is not part of your solution. So you can discard it. However, if we take this original inequality and we put it into Desmos, then it's going to shade the region that does satisfy it. So that's just the heads up. And I do encourage you to check with Desmos and see kind of what Desmos says. Let's see here. Where's my Desmos? And now I've forgotten. X plus 2y is less than or equal to 4. Hey, it even used the same colors as me. Nice. So it does shade the region that satisfies the inequality as opposed to us. But like I said, there's a method to the madness. Okay. Nice. Often I just use these little arrows to indicate the region that does satisfy it, right? And so here I'll make a note. We can use arrows to indicate the region that satisfies the inequality. Just for keeping track of stuff. Okay. We have to graph a system of inequalities. Kind of spoiled it for you. Not really. Saying that this is what we would be doing, but here we are, we're doing it. And so a system of inequalities might look something like this. Now notice that I'm using the same line as we just worked on. And so here, this is from above. From example above. So we already know what x plus 2y is less than or equal to 4 looks like. So what can we do? We could just grab this and put it down here, but let's talk about the others. 4x minus 4y has to be greater than or equal to -4, so we're going to have to draw that inequality as well. And then the reason I only gave you Q1, or the first quadrant, is because of these conditions, that y has to be greater than or equal to 0 and x has to be greater than or equal to 0. Down the line, a lot of things can be modeled this way, and so optimization problems are usually involving kind of materials and labor hours, and so x could be the number of hours that you have, and y should be maybe the profit or something like that of some sort of business. And so then you have positive materials and you have positive profit, hopefully. And so you restrict the domain. And so this is pretty common that we restrict it just to be x and y greater than 0. But let's deal with those first, kind of quick wins. If y has to be greater than or equal to 0, then here I am at y equals 0. And I have to be above this line. If x has to be greater than or equal to 0, same thing. This is x equal to 0, and I have to be on that side of the line. Which means together, I'm restricted to this quadrant so far. Then we can bring down the work that we did up here. So when x is 0, y is 2, we can plot that on here. When x is 0, y is 2. And when x is 4, y is 0. 1, 2, 3, 4. And I can draw this thing. I mean, you're allowed to bring a ruler. I just bet you never thought you'd need one anymore. You don't. You never did. And we said that this is satisfied. And I'm going to move this coordinate here. Sorry, 0, 2. So even without this guy here, we're now bounded, right? We're bounded by this region where all those inequalities are satisfied, but we're gonna add this little guy, this new one. So this is, can I label this 1? Line number 1. Usually oh, clever, nice. Usually I put a label on the lines, and then I don't have to write it out so much, right? Kind of referring to the equations. And because this one is new, I'll use a new color and I'll call it line number 2. So let's draw 4x minus 4y is greater than or equal to -4. And the spacing got kind of weird here. So I'll start up here. So I have enough room. 4x minus 4y has to be greater than or equal to -4. First thing I'm going to do is I'm going to rearrange this into an inequality of y equals mx plus b. And so again, -4y is greater than or equal to -4 minus 4x. Careful here. Whoops, not red. I'm going to have to divide by negative, which means I'm going to have to swap this inequality, which I can do. I can handle that. But I'm going to highlight it. So then -4 minus 4x divided by -4 puts me at 1 plus x. Y is less than or equal to, I'll pull out the -4 because it's kind of late. 1 plus x, yeah, okay. Divided by -4. So y has to be less than or equal to 1 plus x. And I'm gonna just give myself one more line. Recreate the magic. Okay, there. 1 plus x. That's nicer to draw than the other one. They all would have canceled out anyways, right? You could have just picked values of x and y using the original function, but this is kind of nicer to work with. Okay, so then if I let x be, well, my go-to 0, then y is 1 plus x, so y must be 1. Here, it is easy to figure out, okay, if y is 0, then x must be -1. It's easy. Well, I struggle. But then I'd have to draw it over here, which is on here, and that's fine. And so you could do that. Or what I like to do is I just like to kind of pick a value of x that's on here and then plot that point instead. So what can I do when I live in a shoe? Well, let's plot 0, 1 first. So when x is 0, y is 1. And let's get crazy. Let's let x be 4. Why not? You can put in any value of x. Let x be 4. Then y must be 1 plus 4, which is 5. So without a grid, it's a little harder. But if X is 4, then Y must be 5. 1, 2, 3, 4, 5. I'll just do a reference line here. There. 4, 5. Connect these and extend them. We expect it to go through -1, 0, right? Although I didn't put it on here, but we won't be surprised. The inequality, like this part, you mean?
Or any. Know which way.
Well, let's do this one. So if Y is less than the line, then it's going to be all the ones below the line. Now, I know I personally struggle with, okay, I have this line and it's taken practice to know that, okay, the Y's are below the line, so then this area satisfies it, right? These values of Y are greater than 1 plus X, right? Because here you have Y equals 1 plus X, and we want Y less than or equal to 1 plus X. So it's on one side of this line. And so because we want it to be less than, we want this region here. But you can test it. You can pick any point on this side of the line, plug it into the equation, make sure it's true, right? 4, 0 is on this side of the line, right? If Y is 0, 1 plus 4, 0 is less than 5, right? So that's true. Whereas if you pick a point up here, let's do, I don't know, 0.46, right? Then if X is 4, 1 plus 4 is 5, but Y is 6, and 6 is not less than 5, so that's not true. So then you toss it, right? So you can always check your inequality by picking test points, we call them. And they can be any point.
Sure, isn't that putting X or putting Y on the other side? Not way other than using X on the side. Put 1X.
It's only to mirror the Y equals mx plus b setup, which is kind of traditionally how we write lines. But you could absolutely just leave it like this, like in the original. It'll still be true, right? If you put in, well, let's put in 0, 0. If X is 0, Y is 0, 0 minus 0 is 0. Is that greater than or equal to -4? Yes, it is, right? And so, and it is in the region that we were going to keep. So my arrows show me which regions I'm keeping. And so this leads me to the feasible set of a system of linear inequalities. And so the feasible set, or the feasible region, if you prefer, it is a set, but it's also a region on a plane of a system of inequalities is the region that satisfies all the inequalities simultaneously. And so, and I threw in the fun fact. I think we're gonna get there because it is really fun. But in optimization problems, right? So if you're trying to maximize profit usually, or minimize costs, usually they have kind of business applications, or at least they're the most fun to wrap your head around. But then, so optimization is either maximizing or minimizing depending on what you want. And so the optimized solution will be at one of the vertices in the feasible set. And so what can we do? In the feasible set here, if we draw it, the feasible set for that system looks like this. Which is why, I guess if I remove these temporarily, if you discarded all the values that are not in the system, and that's the benefit of discarding too messy. You know there isn't. So then here, this is the feasible set. All those combinations of X and Y are going to solve all those systems in at the same time, right? And so they'll all be solutions and they'll all satisfy all those inequalities. Yeah? And so what's really fun, okay, so all these points satisfy these conditions simultaneously. That's nice. And then in optimization, a fact is that at one of these vertices, so one of those corners of the feasible set, you will get the maximized or the minimized value, depending on what you want. And so I think that's really cool because you can find the vertices, and I'll show you how. And so, of course, the vertices, maybe I'll clarify the corners. And I guess I should clarify optimization. Things like the max or the min, maximize profit or minimize cost are kind of the usual suspects. So how do we find those vertices? The points of intersection. The point of intersection, right, for two lines is the XY point that satisfies the equation of both lines. Right, so I've got two lines, they're crossing, crisscross applesauce. And here, right, that point of XY has to satisfy both the green line and the blue line at the same time. So just one point of X and Y, which means that usually what we do is we can rearrange both equations to be in the form of y equals blah, 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 blah. It doesn't have to be just mx plus b, but that's all we'll be dealing with for now, right? But if you solve for y, then both equations are going to be y equals something, right? So if they both equal y, and it has to be the same y, then couldn't you just set them equal to each other and solve for x? And that's the move. So what we're going to do is let's find the point of intersection for these two lines, y equals 2x minus 3 and y equals x plus 1. So I've got, I kind of think of the y as a gateway. So if I write this first line like this, 2x minus 3 is equal to y. But then that same y also has to equal x plus 1. So then I do it on this side, and then I kind of ignore this y in the middle, right? If a equals b and b is equal to c, then a must be equal to c, right? And so then I get 2x minus 3 is equal to x plus 1, which I can solve for x. And that value of x has to satisfy this equality, right? And so, and maybe I'll scoot this over here. Boop, boop, boop. Solving for x, I'm going to bring my x's to one side, all the non-x's to another side. Do whatever kind of makes you happy. I tend to avoid negatives if I can. 2x minus x is 1 plus 3. 2x minus x is just x. So x must be 4. Which part? Yes. If we're finding the intersection of these two lines, then that's what we usually do. Yeah. No, because it's only true at the intersection. Right? That's not the lines, but you get the idea. So here, I'll show you in Desmos once we have, because now I have the x is 4. And so then it doesn't matter which one I plug in to here. If it's the right answer, then I should get the same value of y, right? 2 times 4 minus 3 is 5. 4 plus 1 is 5. Phew. So now solve for y. So I get 2 times 4 minus 3 is 5. And that's the same as 4 plus 1. That's a relief. So therefore, oops, y must be 5. So the point then of intersection, they intersect at 4, 5. So if I have 2x minus 3 and I have x plus 1, I'm expecting these to intersect, see, yep, at 4, 5. Maybe I'll take a screenshot of this one, bring it in. Might be loud, sorry. Hey, or it might not do it at all. It was very faint. Sometimes it goes out over the speakers. It's really annoying. Okay. Bring this in. Crop it up. Hey, it didn't keep my, so much for that, huh? Well, you have to believe me that this is at 4, 5. I cropped it up. Nice. Okay. So this one, because the graph is so large, you've got a blank graph on the next page. So we're going to graph the feasible set for the system of inequalities, and we're going to find the coordinates of the vertices. So the intersections, obviously. I think it might be nice to try it at least on your own. Give you a couple minutes to try it. I'll pause this here. Okay, good. I cheated. But I didn't. We've done enough practice drawing the lines. It's good practice, so give it a go. But what I want to focus on is finding the vertices. And so, like I was saying, Desmos shades the regions that satisfy the inequality. And so that's opposite of what we're doing. But you can enter inequalities like this, and then you can find the feasible set. I've labeled the vertices because that's our next job, is to find the vertices. So the xy coordinate that satisfies both 2y minus x equals 6 and x plus 2y is equal to 10. Now, what I'm going to do here is, first thing, I'm going to rearrange these lines so to be in the form of y equals mx plus b, just because then it's easier to deal with. 2y is 6 plus x, kind of short on space here, so y must be 6 plus x divided by 2. And then for this line, 2y is 10 minus x, so y must be 10 minus x over 2. So at that vertex, these y's must be the same. So I'm going to force them to be equal to each other. And I'm going to do that over here on the very right-hand side. And so I get 6 plus x divided by 2 must be equal to 10 minus x divided by 2. Whether you multiply both sides by 2 or just recognize that they're both being divided by 2, so you can kind of ignore them. Either way, you're technically multiplying both sides by 2. And so you get 6x, or 6 plus x must be 10 minus x. Moving the minus x over to the left and the minus, or the plus 6 over to the right, I get x plus x is 10 minus 6, or 2x must be 4, so x must be 2. Which, with a graph, is nice because then you can just kind of check to make sure that that looks reasonable, right? X equals 2 looks reasonable. And so if x equals 2 in either one of these, therefore 6 plus 2 divided by 2 is 8 divided by 2, which is 4, which should be the same as 10 minus 2 divided by 2, which it is. So A is at the point where x is 2 and y is 4. Vertex or vertices B and C are a lot easier because they are each of these lines intersecting where x is equal to 6. Right? And so that's nice to have a vertical line here, because then I just plug in x equals 6 and I can solve for y in each of these equations. And so for vertex B, I'll do it down here. Y is 6 plus x, or 6 plus 6 divided by 2. So y must be 6. Vertex B must be at 6, 6. Kind of tight here. And vertex C is also at x equals 6. So y is 10 minus 6 divided by 2. So y is 2. Let's do this. So vertex C is when x is 6 and y is 2. And you can kind of double check all these, make sure that they look reasonable. But then you have the vertices of the feasible set. which is pretty cool. So quite a bit of skills going into it, but with practice, you get. Any questions about the feasible set, etc.? Let's take it back to the slope then. Kind of something we're familiar with. So if you have 2 points, you have a line that passes through 2 points, x1, y1 and x2, y2, as long as they're not the same value of x, because that can't be, then you have a vertical line like this, and that's not very interesting because then the slope is nothing. The slope we can find by taking just y2 minus y1 over x2 minus x1. Actually, doesn't matter which point you assign to be x1, y1, x2, y2, but traditionally we go in order of the x's, right, from left to right, smallest to largest. And so if we have to find the equation of the line through these points, 3, 1, and 6, 0, what's the first thing we're gonna have to do? We have to find the slope. That's a good place to start. Yeah. And then, so let's remember what we're looking for is y equals mx plus b. We need to find, so step 1 is find the slope. Once we have the slope, we also are given 2 points that have to be on this line, so you can use either one to find b. So that's step 2. Okay, nothing to it but to do it. Here we go. Step 1, the slope is y2 minus y1 over x2 minus x1. Rise over run, if you prefer. I don't prefer, because then I'd have to plot these, and I don't like that. But if you prefer, it's allowed. So I'm gonna let this be x1, y1, and I'm gonna let this be x2, y2, just because 3 is less than 6 on the x-axis, so it makes more sense. In that case, y2 is 0, y1 is 1, and x2 is 6, and x1 is 3. Negative 1 divided by 3. So step 1, find the slope. Step 2 is we want to find b, right? But so in step 2, we have y equals negative 1 over 3x plus b. But we also have 2 points that have to be on the line, right? X, Y coordinates. And so here, use either point to solve for b. Let's use the first point, why not? X is 3, y is 1. So then I have 1 is equal to negative 1 over 3 times 3 plus b. Then I can solve for b. Negative 1 over 3 times 3 is negative 1. So b must be 2. I guess step 3 is to put it together. We leave x and y open as variables, of course, because we want to allow for any value of x, and then we can figure out what the value of y is and vice versa. And so step 3, y is mx, so negative 3x plus 2. And that's the equation of the line through those 2 points. So I can give you 2 points. You can find the equation of the line. Much like how if you have a line or the equation of a line, you can pick 2 points to find, or pick 2 values of x and find the value of y. That makes that true. What does it mean? So perpendicular lines we're familiar with, probably, right? They intersect at 90 degrees like this. So that's a fact. And so the perpendicular property in terms of the slopes, what it means is when 2 non-vertical lines, so they can't be like this, are perpendicular, their slopes are negative reciprocals of one another. So if 2 lines with non-zero slopes m and n, let's say, are perpendicular to one another, then m must be the negative reciprocal of n, so negative 1 over n. Of course, if you're able to prove that 2 slopes are negative reciprocals of one another, then you are allowed to conclude that they are perpendicular. How I like to use this is, what if I give you a line and you have to find the equation of the line that's perpendicular to this line that passes through some point? That's testing, okay, do you know what it means to be perpendicular in terms of the slope? And so let's start there. In this case, y equals 2x minus 5 is my original line. And if it has to be perpendicular, I'm going to start with the slope, just like I did up here, right? And so then the slope must be negative 1 over 2, right? Negative 1 over the original slope in order for it to be perpendicular. That's nice. Now I have the same scenario as I did earlier, right here, where I can solve for b because I have 1 point that it has to pass through. This new line has to pass through. So this new line, y equals negative 1 over 2x plus b, has to pass through 1, 2. That's a condition. So I'm going to use that. So 2 must be negative 1 over 2 times 1 plus b to solve for b. So I get 2 plus 1/2 is equal to b. So b, let's be proper and write 5 over 2. If you did 2.5, that's fine, or 2.5, that's fine too. But if you deal with the fractions, common denominators, that kind of thing, you get 5 over 2. So therefore, y is negative 1/2 x plus 5 divided by 2. Nice. Parallel lines are easier, right? If they're parallel like this, then they have to have the same slope. And so that's nice. So parallel lines have the same slope. And of course, if you're able to find that 2 different lines have the same slope, then you're allowed to say that they are parallel, right? So it works both ways. We have to find the equation of the line through 2, 0, and parallel to the line y equals 1 over 3x minus 11. Well, then I know m must be 1 over 3, whoops, because that's the slope of the original line, so it has to be the same. and y equals 1 over 3x plus b, it has to pass through to 0, which means that 0 is 1 over 3 times 2 plus b, which means b must be negative 2 over 3. Therefore, y must be 1 over 3x minus 2 over 3. I'd encourage you to check all these in Desmos just to make sure that they kind of look reasonable, right? But we've got absolute value functions to tend to. Any questions though before we keep going? Okay. So the absolute value function is a piecewise function. You guys worked with piecewise functions? I can't remember if we have. I don't think so in this course. But at this point, it's all kind of a blur with my other courses, so who knows? But a piecewise function is if we have, no, I think we have. If we have different domains, right, or different functions on different parts of the domain, we can break up the domain and the function behaves in different ways. Now, the absolute value function, it really just turns a negative positive, right? So it just returns a positive value, and the graph of the absolute value function is a v. So if x is greater than or equal to 0, then y equals x is the function. If x is less than 0, not equal to 0, then it's going to return negative x. So you get this f of x is negative x on the other side. Okay. And so what we're going to do is to solve absolute value functions, we're going to consider both the positive and the negative version of what's inside. Okay. You are allowed to consider the positive and the negative version of f of x, but I'm not going to. And I don't know why I feel like it wouldn't work. I haven't found a situation where it doesn't work, but it's just kind of ingrained in me from, I don't know, math. And so I only do it for, so notice here, the absolute value of x are these vertical bars around x. And so here, this is the absolute value of x. And so it takes whatever's inside and it returns x if the inside is greater than or equal to 0, or it negates it if the inside is less than 0, right? Making it positive. So what if we have to solve? I'm kind of showing you by example. If you have to solve the absolute value of 2x minus 3 is equal to 8, okay, then what we're going to do is we're going to consider first 2x minus 3 is equal to 8, but we also have to consider the negative version of the inside. And so then negative 2x minus 3 is equal to 8. So here's what I mean by, okay, I'm going to negate whatever's on the inside. Could you divide by -1 to the 8? Sure. So I don't see why it wouldn't work, but I was just raised that you always negate the inside. But you could technically I guess, move this negative onto the -8, and maybe that's a little bit easier. But I'll stick to my guns, because otherwise I'll get confused. So now I'm going to find two solutions. Okay? And so let's see here. 2x minus 3 is equal to 8. Well, the math there is not bad. 8 plus 3 is 11, so x is 11 over 2 is a solution. You can plug it in, right? 2 times 11 over 2 minus 3 is equal to 8. That's true. What about the other little guy? If I expand this negative inside, I get negative 2x plus 3 is equal to 8. So then negative 2x is 8 minus 3, which is 5. So x must be negative 5 over 2. Let's try it. Negative 5 over 2 times 2 is negative 5 minus 3 is negative 8, but the absolute value of negative 8 is 8. So it still works. Okay. Let's graph this thing to really talk ourselves into it, I guess. So the absolute value, there is an absolute value button on Desmos down here of 2x minus 3 and that. Now I could set this equal to 8, but then it draws lines where it's true. It doesn't really draw it the way I want it to. So I'm going to draw a line at y equals 8. Oops, 8. There. So what this thing looks like and what we found is that at negative 2.5, the solution is 8, and at 5.5, the solution is 8. Which we did, but we used fractions. Let's see. Can I, copy and delete. Spicy. Copy. Paste. Allow paste. Score. Maybe, just maybe, I won't have to have a bunch of screenshots then. That's nice. So for absolute value functions, we're typically going to have two solutions. So that's kind of fun. What if we kick it up a notch? 4 minus 2 times the absolute value of x minus 1 is equal to 1. We only know how to deal with the absolute values. And so what you're going to do is you're going to isolate the absolute value function. So move everything else to the other side, and then we can deal with the absolute value. So here, need to isolate the absolute value of x minus 1. So we have 4 minus 2 times the absolute value of x minus 1 is equal to 1. First, I'm going to subtract 4 from both sides. I get negative 2. Absolute value of x minus 1 is 1 minus 4. Does that match? It does. Okay. And then divide both sides by negative 2. So I get the absolute value of x minus 1 is negative 3 divided by negative 2. Negative over negative is going to cancel. Absolute value of x minus 1 is 3 over 2, or 1/2 if you prefer. So then I can take this absolute value of x minus 1 is 3/2. And I can work with the positive version of the inside and then the negative version of the inside. Or if you want to find them in the order that they appear on the graph like this, you would do the negative one first and then the positive one. It really doesn't matter. So x minus 1 is 3.5. So x must be 3/2 plus 2/2 is 5/2. And negative x minus 1 is 3/2. Negative x plus 1 is 3/2. 3/2 minus 1 is 3/2 minus 2/2, so 1/2. I get x is -1/2. Once I bring that negative over. You can graph that to check it, but I'm feeling pretty good. Maybe I'll highlight these guys to show that there are two answers, two solutions. What about the absolute value of x minus 4 is equal to -2? That can't be, right? Because the absolute value only returns positive values. So here, there are no solutions. Since the absolute value of x only yields positive values. So kind of tangent to that, I'll do a little separator there. There are three possible results that we can get. So in fact, there are three possible results. As an example, consider the horizontal intercept. Which is where y is equal to 0. The three scenarios that I could have of a generic absolute value function, which could look something like this. If I'm concerned with the points where it crosses y equals 0, right, the horizontal intercept, well, in this case, it doesn't cross it ever, right? And so that's kind of what we have here. Right? And so here we have 0 horizontal intercepts. Can I abbreviate this HI? I will. Because it never crosses the x-axis. Another scenario, a rare scenario, would be when x is, or when the inside is 0, then you're only touching at the vertex of the absolute value function. And so then here we've got one horizontal intercept, right? If the inside of the function is 0, then you get y equals 0. So here we have one horizontal intercept. That's pretty rare. Usually we have something like this. It could be facing up, it could be facing down, right? Or maybe something like this, just to show you the two typical scenarios. Either way, it's going to cross the x-axis. And so in both these scenarios, we have two horizontal intercepts. Okay. All right. You didn't want to get back to it, did you? You don't want to get back to it. Let's do this last one. And then I'll leave the next page for next week because I'm not crazy. We are out of time. If I ask you to find the horizontal intercepts, really what am I asking? I'm asking you to find where does this thing equal 0? Okay. Can do that. We know how to work with this now. And so we have 5 times the absolute value of x minus 2 minus 3 is equal to 0. I have to isolate the absolute value. So I add 3 to both sides. I get 5 times the absolute value of x minus 2 is 3. So the absolute value of x minus 2 is 3 over 5. I have to consider the positive and the negative version of the inside. So here I've got x minus 2 must be equal to 3 over 5. That one's relatively easy. I have to add 2 to both sides. Common denominator. Now I have a little bit more room, so let's do that. 3 over 5 plus 2. But I need a common denominator, so my go-to move is just multiply by 5 over 5. I'm allowed to multiply by 1. Doesn't change. 2 times 1 is still 2, as long as you do it to both sides. So then I get x must be 3 plus 2 times 5 is 10 over a common denominator of 5, so 13 over 5. I'm pretty sure if you have the engineering calculator, it'll just do your fractions for you, right? You don't have to find the common denominator, but it's a nice skill. And negative x minus 2 has to be 3 over 5 as well. So I get negative x plus 2 must be 3 over 5. So negative x must be 3 over 5 minus 2 times 5 over 5. Three minus 10. I'm going to go with negative 7 over 5 divided by negative 1. The negative goes away. X is 7 over 5. Try this page on your own for Monday. I see you this Monday, not next Monday. I got a little panicky. You've got inequalities here. but you can do it. You've got the skills. All right. If you have any questions, let me know. Otherwise, have a wonderful weekend and I'll see you on Monday.